In this lecture, we're going to talk about doing double integrals in polar coordinates. And let me start by first reminding you how polar coordinates work. So let's say you have a point in the plane. Usually, you would specify that point with an x-coordinate and a y-coordinate. And you can really think of the y-coordinate as being the distance from the point to the x-axis, whereas the x-coordinate is the distance from the point to the y-axis. In polar coordinates, you instead specify two different pieces of information. You specify how far the point is away from the origin, this distance r, and the angle, theta, that ray makes with the positive x-axis. And in polar coordinates, you have the following equations that relate x and y to r and theta that just come from looking at the right triangle relations. So you end up getting that x is r times cosine of theta, y is r times sine of theta, and that x squared plus y squared is equal to r squared. You can also even throw in an additional relation if you want, that tangent of theta is equal to y over x. Okay, and what we'll see is that for some regions in the plane, they're more convenient to describe in terms of polar coordinates instead of using the ordinary rectangular coordinates. So maybe let me just sketch an example of a region like that. So here in the first quadrant, let's sort of take a couple rays out from the origin at two different angles. And let's take some circles of a couple different radii. And now let's look at this region right here, this sort of sector of a circle. So I have two different radii, maybe a radius of A and B. And so my region lies between two circles of these radii. And then I have these two angles. Maybe this first angle here we might call alpha. And then this bigger angle here we might call beta. So I can describe this in polar coordinates by saying r is between A and B, and theta is between alpha and beta. So this is what we call a polar rectangle. What makes it a rectangle is that the bounds for r and theta are constant. Of course, it's not really a rectangle in the sort of conventional sense, but we'll see that regions that can be described as polar rectangles are easier to integrate in polar coordinates. Because imagine now that you wanted to integrate a function over this region using the ordinary rectangular coordinates. So typically what you would do is you would try to slice it either vertically or horizontally. But if I slice this thing vertically, then you'll notice that some rays will start off on this circle and end on this straight line here. Or they might go from this line to this circle. You end up having to cut the region up into a bunch of different pieces if you want to try to slice vertically. And similarly, if you try to slice horizontally, you end up having to split the region up into different pieces because the left boundary is sometimes this circle and sometimes this line. Okay, so let's undo those. So then how can we actually integrate things in polar coordinates? So the idea is going to be that if you had a region in the plane, even something more general than a polar rectangle, maybe what you have is you have some curve of the form r is a function of theta that describes some sort of fan shape here for some range of angles. Well, when we developed the idea of a double integral, we were taking regions and kind of splitting them up with a little grid, right? We would sort of draw a bunch of vertical lines and a bunch of horizontal lines, and then we did a double Riemann sum over those little individual rectangles. But for a region like this, the kind of grid that makes sense is a polar grid. So a polar grid is one where instead of sort of vertical and horizontal lines, well, you have sort of arcs of circle of different radii, and then you have rays shooting out in different directions, right? You get something that looks kind of like a radar screen. And so the idea would be that you would want to split your region up and kind of approximate it by pieces that look like these little, well, these are polar rectangles. And then if you wanted to actually make the, sort of do the double integral, say you wanted the volume underneath some surface but above a shadow that looks like this, well, still you want to do something that looks like add up a bunch of f of sample points times the area of whatever one of these little pieces is, and then take the limit of that as the number of pieces goes to infinity. Right, I'm leaving out some of the notation here. I'm keeping it kind of breezy, but this is the basic idea. So let's look at this factor right here. What is the area of one of these little pieces? Well, so we have, again, sort of a polar rectangle, which is, say, in between two circles and in between two rays here. And so this distance between the two radii, let's call that distance delta r, right? It's a difference of r values. And this little angle right here, let's call that delta theta. It's a difference of two little angles. So how does the area of this region depend on delta r and delta theta? Well, first of all, the thing you might guess is not the case. It's not just the product of delta r and delta theta. Right? In rectangular coordinates, that's what you do. You take delta x times delta y, and that gets you the area of the little rectangle, but here that doesn't quite work. And the reason is that the area of one of these little pieces depends not just on how far apart these circles are and how far apart the angles are, but actually on how far out that kind of rectangle is from the origin. Sort of the further out that it goes, the bigger it gets, the larger the area is. In fact, we're going to see in just a minute that the area of one of these pieces is r times delta theta. Well, let's kind of zoom in and make that a little bit clearer. Well, let's start by just looking at a piece of a circle. So if you want to know what the area is of a piece of a circle that looks like this, I know it's kind of a terrible drawing, but let me erase the sort of ugly parts here. There we go. So here I have an arc of a circle. Say it's a circle of radius r. Say r is this radius here, and I have this angle, which we were calling delta theta. So what's the area of that piece right there? Well, the area is just a portion of the area of a full circle. So it's going to be something times pi r squared. And what is the something in this case? Well, I have an angle of delta theta. If that angle were 2 pi, then I'd have an entire circle. So what matters is what fraction of 2 pi this thing is. So I look at delta theta over 2 pi. Well, the pi's end up canceling then. You just end up with 1/2 r squared times delta theta. You might even remember this from calculus 2. You may have found the area enclosed by a polar curve, and you ended up integrating 1/2 of r squared in order to do that. So this is the area of a whole segment of a circle. But now what happens if what you want is not this whole thing, but actually you want just sort of a segment that includes the top part? right? Like, let's say now you want the area of this, where I have kind of like an outer radius, which is here, and inner radius, which is here, and maybe I'm just going to call the kind of radius in between them. That's what I'll call r. Okay, well now I need to kind of update this. So now the area that I had before was for the area of this entire slice. So the entire slice is now using what I'm calling r out. So that's the area of the whole slice. Well, so if I want the area of just this top part, what I want is kind of the area that uses the outer radius minus the area of this sort of little sub-slice that I'll color in blue here. Right, so this slice right here, if I do the big slice minus the blue slice, then I'll get just this kind of red topping. So that's going to be 1/2 of r inner squared delta theta, right? Just the area of the outer minus the area of the inner. Well, those both have a factor of 1/2 of delta theta. So if I factor that out, well, now I have the difference of two squares, so let's write that as r outer minus r inner times r outer plus r inner. And r out minus r in, that's what we were calling delta r. So that's delta r. Here's delta theta. What I'm left with is 1/2 of r out plus r in. Well, that's just the average of r out and r in, and that's this middle r value, r. And so you end up getting just r times delta theta times delta r. If I were being a little bit pickier, maybe I'd use a different letter instead of just r here. I'd call it something like ri star. It's sort of like a sample r value. But in any case, you get this extra factor of r when you go to find the area of a polar rectangle. So then, what happens when you go to integrate something using polar coordinates? So that means that to integrate something, we want the integral of f of x, y, dA over some region. And we want to integrate in polar coordinates. Well, first of all, you have to represent d in terms of polar coordinates, in terms of r and theta. Often that's going to be a polar rectangle, right? Often it's going to be something where r is between a and b, and theta is between alpha and beta. Most of the time, if you can't do that, you probably don't want to use polar coordinates. Then we have to convert the function itself to polar coordinates. So convert f to polar. And you do that by just changing every x to r cosine theta and every y to r sine theta. Although you should be careful, because if you have an x squared plus y squared, well, you can do this transformation and that's not wrong, but if you simplify it, eventually you just get r squared. And so it's easier to just try to remember that x squared plus y squared becomes r squared. And finally, you're going to change dA, not just to dr d theta, but to r dr d theta. Right? And this r is sort of pops up here for the same reason as it did in the area problem we were just looking at. Okay, so that's the sort of high-level picture. So let's look at some examples to see how that works.